Hello and welcome to this webinar. My name is James Schwieter. Give me just a second. I'll show my webcam so you can see my beautiful balding head. All right, so today we're talking about avoiding costly collisions and simplifying your MacroB programming using VERICUT. I'd like to take just a minute and introduce myself. I'm a technical support engineer for CGTech. CGTech is the company that offers the VERICUT software, among several other software addition packages to the base VERICUT. All right, I'm going to turn my webcam off now so that you can focus on the presentation, and we'll jump right in. Again, thanks for joining us, and I want to thank the NTMA for allowing us to host this webinar. All right. Just a little bit about CGTech. We are headquartered in Irvine, California. This gentleman right here in the middle is John Prune. He started the company in 1988 and is still running the business to this day. All right. So at the end of this webinar, we will have questions. There is a box, a question box that you can ask questions at any time by typing them in, and then the meeting moderator will read those at the end of the presentation. So collision checking in the VERICUT software. What is a collision? Let's define what that is first. And to do so, I have a little video here that I'm going to show.
Go! Ow!
All right, so hopefully that was helpful in distinguishing what a collision or crash would be on the machine. That second to last one there is what we call unintended fusion welding. So what do collisions cost? Well, obviously with all programmers, it costs us our pride. All kidding aside, really safety is the top priority, and safety is one of the first things we want to prioritize when we're running a machine. And then collisions cost us money in various different aspects of the manufacturing process, whether it be in machine repairs, tool replacement, or missed opportunities with machine downtime. So we want to avoid collisions at all possible. How does seeing red save green then? Well, in the real world, money or cash for you Bitcoin fans is green. Inside VERICUT, collisions between models are displayed in red. So seeing red in the VERICUT virtual simulation will allow you as the programmer to make corrections before the company ends up spending green in the real world. And it is at this time that I bring the unfortunate news that money trees do not exist. If you do know where they are, please let me know after this presentation. So what's necessary for collision checking inside of VERICUT? Well, we're going to need the machine models from the machine tool builder, your fixture and stock models, and then your tool assembly models, all your holders, your cutters, and more in today's world, you can get these directly from the tool manufacturer via various different methods. We will not discuss those methods in this presentation. So the next thing we're going to need is the machine kinematic structure, which in VERICUT we define with components. Suffice to say, is it a horizontal machine? Is it a vertical machine? how does the X and Y axis interact with each other. That way we can correctly mimic the motion and therefore have accurate collision checking. And then once we have that kinematic structure, we need to know the rules of engagement. What are our collision settings? And last but not least, because we all know that the real machine doesn't do anything that we don't tell it to do, we're going to need the exact NC program that's going to be ran on the real machine. All right, so there's two types of collisions here. The first being project or setup collisions inside the VERICUT software. And this is going to be anything that changes with the job. So it could be your vices and your holders, so your tool assemblies and your fixtures models. And then we have machine collisions, and typically we're going to consider these between actual pieces of the actual machine and some other component. So in this case, we have a spindle housing colliding with a vise. So we have the machine component being the spindle housing, and then the fixture being the vise. And sometimes things catch on fire. Very bad. So how do we do this? We talked about the having an understanding of telling it, how to set up these collisions. So we can do that inside the project for collision checking. And you'll notice here, this is what we call the project tree without giving you too much of a training in this presentation. And down here underneath our setup, we have a collision tab. And inside of there, we can set up several different setup collision checks. And we also have a near miss window, so you can apply a holder tolerance for a collision check unless you like living life on the edge and you want to check everything to net. So this near miss window applies some real world machining and manufacturing tolerance allowables to be accounted for. So here we have a holder component, and inside VERICUT we get an error message that says that this holder component of this tool assembly, in this case it's tool 1, has exceeded the near miss tolerance with the fixture component being the vise. So what about those machine components? How do we configure those? Because they are machine components, we're applying those with in the machine itself. So here we have our kinematic structure that I talked about being a necessary component after you have the machine models. So in this machine, we've got the B axis associated to the Z, and then the other part of it would be the X, Y, and the spindle. So here in our machine settings, we have a collision check between the Z component and the X component. Okay, so you can see here the two parents of the two different portions of the machine kinematic structure. What we're going to do is we're going to apply, we want to check all of the components axis associated to the Z-axis against all of those against the X-axis. And so when we do that, we have collision checking between all of these axis and components and all of the X, Y, and spindle, this being a mixed type machine. So here you can see that when we highlight each collision check, you can see it highlights the components with the associated models for those and what we're checking against. So we have the Z-axis and all the other components, including your fixture, against the spindle housing and the X and Y axis. So if we do encounter a collision, inside of the VERICUT software. How do we know that? What do we do? You'll end up with a message in your logger window at the bottom, and then you can select on that message in the logger, and it's going to take you exactly to the line in the program that caused the error. Also, we have a status bar that shows there's a collision button that will turn red whenever a collision occurs, and it will pause the simulation there. All right, so now let's see how all this works. All right, so here we have a machine here. We've got our, without going into too much detail, we've got our machine kinematic structure here. That's all done. We've got our offset set up. We've got a program here. And this is the same program we're going to run on the real machine. I mean, this is a demo of collisions, so do not run this on the real machine. But let's take a look at the collision tab that we looked at in the presentation slide. So here we have a couple settings. So I'm going to turn this off between the fixture and holder, and we're just going to see what happens here. Okay, so the first thing we notice is we have an error message here in the logger, and it's telling us the tool holder exceeded this near miss with the fixture. I'm not going to go into details about where this error message is coming from, but once we have it, we can select on it and see exactly in the program what caused it. If we wanted to take that a step further, we could turn on our NC review. And notice every time it encounters a collision, it pauses the simulation. So now we can scroll back in the program and actually see the motion block that caused the collision to occur. So, all right, so now let's reset. Let's change this, and let's go ahead and put in a tolerance here of 150 thousandths. That's pretty gracious. Now let's see what happens here as we play the simulation. So we're machining the part. All right, so now we get a error message that says that the near miss tolerance has been exceeded. So we know that if our holder assembly or maybe our vise assembly has a given manufacturing tolerance or machining tolerance, and we want to account for that, we can certainly do that here in the configure collision window. So let's go ahead and see. So this is a setup collision. So let's go ahead and let it continue on past that. Turn this stop condition off here. You'll see that we can stop the simulation at collisions. Okay, now we're working on the other side there. And you notice I turned that collision stop off, but the logger is still logging all these errors. And we see here that the fixture component exceeded the near miss with the y-axis. So we can turn on our review mode and jump down here to see that. And we can see, oh, yep, the vise itself is getting ready to collide with the spindle housing, of course, which it does end up doing as we play past that. So at this point, you'd already want to be making corrections to your program to account for these. If this was occurring on the real machine, you would already be at least out a vise, potentially have damaged the spindle, especially on high-speed spindles that use ceramic bearings, or at least calling in maintenance for a good day of realigning the machine and calibrating everything back in. All right, so the last one is, I don't know if you saw this from the video or remember it. There was a picture of a high-speed steel drill going into a part at an angle while the part was moving. And so what I've done is added a drill here, and we're just going to simulate that and see if VERICUT could catch a drill trying to make a hole while another axis aside from along the tool axis, which is Z. So here we're going to position down into the part. And you'll notice, of course, there's let's say I manually edited this program. I forgot to move the X direction down to the next line, so it's moving with the Z axis. We can see that in the part here. We can take a closer look. Here we can see that. And then down here at the bottom, of course, we have an error message, and VERICUT's telling us, hey, this drill tool 3 loaded in this component contacts the material in a motion that's not parallel to the tool axis. And then, because we're helpful, the message lets you know that, hey, a drill can only cut in a motion that's along the tool axis. So just like that video showed on the real machine, VERICUT can detect that type of, not necessarily a collision of sort where you have two components colliding, but a collision in the fact that a Z-axis only tool is now being in contact with material along another axis at the same time. All right, so this concludes the collision checking portion of the presentation. We're going to transition into MacroB Programming. Again, if you have any questions over the collision checking, you can certainly ask those questions, and we'll try to get to them here at the end. So what is MacroB Programming? Well, it's FANUC's version of parametric programming. Yes, I said FANUC. You say FANUC, potato, potato. I don't know that they've released an official press statement on how to pronounce their name. I wish they would. So what are the components to MacroB before we jump in? And this is just brushing the surface, but I thought it would be important so that we're all on the same page here. We've got main and possibly subprograms. It all depends on the structure of the program that you're running. Variables, macro functions, branching and loops, and of course, that's it. It's that simple. But if you've ever done MacroB programming, you know that all of those components can add up to be somewhat frustrating. So let's take a look at each one of those components just real briefly here. Types of variables. So not only are there variables, there's different types of variables. We've got local variables. We've got common or global variables. And then we've got system variables. And obviously, to do MacroB programming, you do need to have, you're going to already have some understanding of what these are. So I'm not going to, this isn't a training on MacroB programming, but there are differences between those, and we can check for that with the VERICUT software. Different macro functions. We've got addition, subtraction, multiplication, division. We've got our trigonomic ones. We've got our logical, whether it be the Boolean or the bitwise. And then we've got miscellaneous, absolute, square root, rounding value. All these things are inside or can be associated to MacroB programming. So how does VERICUT help us make MacroB programming simplified? How does it help us complete a MacroB program and know that it's going to run correct on the real machine? So what we're going to do is now break that down and kind of go back through those and see how VERICUT can assist at each step. Subroutine nesting. When you start adding subprograms, there's different nest levels, and it can become confusing, especially when you're just writing the logic in Notepad, or if you're using a Notepad++ or some other type of editing, or if you're doing it on the real machine, it can be confusing, and you can quickly lose track of how deep or how many levels of subroutines you have and what level you're currently at. So the call stack inside of VERICUT allows us to see, this is my first program, and at this line I called this subprogram, and this is the subroutine that's called, and this is the line that we're currently on in that sub. And I'm going to show this in a demonstration at the end. Suffice to say that we can quickly look at this and know that, oh yeah, we're 2 levels deep. It is not that easy to do on the real machine, or even just looking at your logic on paper. So here is in the main program where we called the sub. All right, so variables. We talked about variables. There's all sorts of variables, different types of variables. Some of them you can read from the page on the machine, but system variables you can't if you're on the real machine. So you have to write those to either a common or some sort of global variable that you can then go read. And what I'd like to say at this point is keep in mind everything that I'm showing you inside of VERICUT. Think about debugging or trying to figure out this information on the real machine. The whole time that you're physically standing in front of the machine and going through a macro program to verify it, to validate it, to get the correct variables, to use the correct values, the whole time that you're standing there looking at the control is time that the spindle is not running, making chips, making the company money. And that's really one of the biggest things that's not really captured in this presentation, but just keep that in mind that if you're proving out your macro program on the real control, it can be done, but it's costing you more than just what you think it is in terms of your time. Spindle time, uptime is a huge thing in the manufacturing industry. So, all right. So all variables inside of VERICUT, we can see the global, we can see common, and we can also see and read system variables, unlike the real machine. There's an additional option, so especially when you're doing macro programming, I don't want to look at all the variables that are in the machine control. All I want to look at are specific ones that are specific to what I'm working on. So I can select those and add them to variable tracking, and I'll show that. I'm not sure about you, but if you've ever worked with macro programs and doing branching and loop logic, one of the biggest headaches to run into is missing a bracket in an if statement or a while statement, or having 2 decimal places when you should only have 1. And it's just, you beat your head against the wall when you're down at the machine, you're taking machine time, and you're trying to figure out what's wrong with your complex logic, only to find out that it was a simple bracket. I mean, it is so frustrating. So inside VERICUT, we have the NC program syntax check. And what we can do here is we've got several default options, and you can also define your own syntax error checking. So before you even run it inside VERICUT even, now I can run a syntax check and say, oh yeah, I missed part of my if statement, or I missed a bracket in my if statement, or I had an extra decimal place right out of the gate. No need to even get down to the machine and waste time even walking down there and back up only to change something simple like that. So there's a list of different errors you can do, different syntax checking, and we'll take a look at this option here in the sample. As you can see, when you run the check syntax, it gives you all the different types of syntax errors, and then you can actually see what line those occur on. So here we have 2 decimals behind this Y value of 4. All right, so this is, I had a lot of fun creating this demo, so I hope you enjoy it. Then this is going to be a little bit technical. So for those of you who aren't familiar with MacroB, come at it with an open mind. It's very useful, but it can get quite complex. And so what I've done is I've created a macro program, and it's exclusively macros with branching and subprograms and variables of all sorts and types. So I really wanted to showcase what VERICUT is capable of. And I did want to point out that this is just a standard FANUC 32i control that's included in our library controls. So there hasn't been any customization to support this functionality. It's there right out of the box. So what we have here is, here's our machine, of course, and then I've got a workpiece view so we can see it more clearly. And this is just there's nothing fancy here. There's no helical motion. All we're trying to do is put some standard circles on a flat plate. But because it's so simple, I don't want to create geometry inside of a CAM system and then generate the G code and then run it on and then I have another base plate that has the same feature, just a different size, maybe in a different spot. Now I have to do that whole process over. With a macro program, I can just simply come in here and change values, run the program, and I've got a whole different part just by changing some variable parameters. So that's the enticing part of MacroB programming. So let's briefly take a look at this, and then I'm going to play the simulation just so you can see what's going on here. So the features that we want to machine is a circle, of course, and that's a 2-inch diameter. We're going to be using a 1/2-inch diameter tool, and then we're going to use G55, 3000 RPM, and there's a couple other parameters here, but I want to show that we're going to be running 6 total parts is what we want to do here. So let's go ahead and reset, make sure I've got all my stop conditions turned off. And you can see just like that, I've created 6 holes. And let's take a look. What we wanted to do was we wanted them to have a depth of 300 thousandths. So if I come into my X caliper and take a measurement here, we can see that that is indeed 300 thousandths. There. And then another thing that I wanted to point out here is that we have a spacing parameter between these sets of holes. So let's take a quick look at that. So we have spacing in X. If we look at our coordinate system here, we've got X and Y. This is a horizontal machine. And so our spacing in X, we want to be 0.5. So if we do a model thickness using X caliper inside of VERICUT, and I get kind of close, again, it's on a circle, so I could change my rounding here to better show that measurement. So there we have 0.5. I didn't do a very good job there taking the measurement. 0.5 and 0.5. Let's check the spacing in Y. We have 1 inch. All right. So let's just take a close measurement here. 1 inch, 1 inch, 1 inch, and 1 inch. Just keep in mind that if you were to test this out on the real machine, not only would you have spent time at the control creating this program, proving it out by cutting air, so you've got time wasted cutting air with the spindle just to verify that everything is correct. But even that doesn't verify it exactly, right? You don't know for certain that the features are going to be machined exactly how you want them to. So then you're going to load a piece of scrap material or maybe start your first base plate, and you find an error, the hole diameter is not correct. Let's take a look at that. We've got a 2-inch hole. So there's numerous things that we're saving here by checking this and doing this inside of VERICUT. We're not wasting material, we're not wasting spindle time, and we know before we even run down to the machine that all these parameters are working and these programs work. Okay, so let's just show the functionality of this. So let's change this to 4 for a total of 4 holes. And then I'll kind of show what VERICUT can do. So now we have 4 holes, and I just changed one thing. If you were programming this in a CAM system, of course, you would have had to go back, change your geometry, repost it, and start over again. Let's change the RPM. We can change that here. I'll just do that real quick. And then let's change the holes to 3 holes, and we only want 1 hole in X, so we should get a row of 3 along the y-axis being up. And of course, we got 3 holes. If we put in a stop condition so you can kind of see the spindle RPM. Okay, so let's take a look here. We've already called our spindle RPM. We're actually using a local variable. So if we take a look here, where are we at? So remember I mentioned the call stack. So right now we can see without any trouble at all that we're 3 levels deep inside of Nest programs. At the same time, we can see that we called the second level using a G65, and that the S value, so the local variable, is using variable 804. So we can pull up our variable page here. And if we take a look at 804, we can see that that's 2000. We have a description of it, which you wouldn't have in the real machine, right? This field doesn't exist on the macro variables. But I don't want to look at all of these, all the machine variables and all the variables. So what I've done is I've moved a couple of them over here so we could copy, let's say we wanted to add this, we can throw this into their variable tracking, and here we can see it just right there. So let's see if the status, let's check the status. We want to know, did the machine actually use 2000 RPM? And sure enough, with our M3 command, we can see that it's going clockwise at 2000 RPM. All right, so let's turn this off. Let's reset. So hopefully that shows you, I don't know if you've ever used sub-programs in nesting, but this call stack is huge for not getting an error on the control saying that you've exceeded the nest limit for subroutines. Okay, now let's say that another part of macro programming is error messages. Because you're an avid MacroB programmer and you've built in error checks and you fat fingered a negative value for the diameter of a circle. Now there's no telling what that would do on the real machine, or we could check that in VERICUT. But in this case, I've built in a check and we want to see if the error message logic is working correctly. And as you can see down in the logger, we get error 3000, and it tells us, hey, the diameter must be positive. And if we come over here, we can see that we had a check message to send us down here, hey, if this pound 1, which is our 800, if the tool diameter, or if the hole diameter, excuse me, is less than or equal to 0, then go to 951 and then give us an error message. And this is all stuff that you're going to be programming and adding. So if you want to validate or verify your error messages and your logic for those, then VERICUT is a great way to do that. Here we have a combination of Boolean and bitwise functions. So we have our first condition, an OR statement, and a second condition, and then a goto. So VERICUT supports all of this. All right. So let's do something here. Let's change this. Let's say we forgot a bracket, and I'm going to save this. So the question is, before I get to the real machine, I want to know that I've done everything correctly. I talked about the NC program syntax check. So what we're going to do is we're going to run a syntax check. I'm going to open the settings, and we're going to see that I've got an unbalanced number of parentheses, and that our comments are excluded, right? Because we're not using parentheses, we're using brackets. So we hit OK, we're going to check all. And sure enough, VERICUT found that on this line, there is a missing bracket. And you notice that there's two separate errors. That's because there's two different syntax checks happening at the same time. This also happens to be an if statement. So we have a missing bracket on an if statement. And then in general, we have an unbalanced number of brackets on this line to begin with. So if I come back in here and add a bracket back, and then save this, close this window, reset our simulation. Okay, let's check it again and see what happens. And you'll notice that the check syntax didn't find any errors. Just wanted to show that another thing, we talked about system parameters and system variables. So what we have here is a dual two loops. We have two while loops, and inside the second while loop we have a G65 call. We talked about local variables. So what I'm going to do is I'm going to put a stop here, and I'm going to play the simulation. I just want to see what we're passing on to the subroutine. So I can come to my variables, and I'm going to scroll down. And here you'll notice that inside sub, that's what a local variable is. So now I can see all my local variables and all the values that were passed to that. And if I want to associate with these, I can open my call stack here, and I'm going to see that on my G65 line, here's my G65 line. I can see all my parameters. So for A, I passed pound 800. So pound 800 must equal -2. If I go to my variable tracking, I didn't add it to my variable tracking here. Let me just scroll down to it. Pound 800 is indeed -2. Hopefully you can see how the interaction of call stack and your variables, where you can see your local variables and see your nest level, can really expedite proving out your MacroB program. I'm going to change this back. So we're going to jump into this sub. And what I wanted to show was here we have another subroutine. So currently we are one level deep, or at the second level. And if you're not paying attention, it's very difficult to understand where I'm at. If you just click cycle start for your macro program, you may not know where you're at. And here we can see, okay, so now inside of this, we have another while loop with a do statement or do loop. And so we're able to do actual radial passes. So we're radially stepping over, and then it steps outside of this subroutine, and our M98 is passing on our local variables from the G65, and we're stepping down in Z and then making another pass, axial pass. And then here we're going to, you can see that we're updating our G55 X system variable. And so watch what happens. Let me reset, let me change this back because we've only got one hole in X. Let me save this. All right, so now we expect 3 total holes, 2 in X, and then another one on the second row. So let's get back to that spot there. You can see the machine view in this one. All right, now let's just step in here. So we can see this is our while loop 1. So what we're doing right now is we're verifying a while loop 3 levels down inside of a subprogram. Doing this on the real machine requires the use of single block, similar to what I'm using a single step here in VERICUT. But again, this can become very tedious on the real machine and take up a lot of time. So you can see that radial pass there, and then we're going to step down in Z and verify that. Okay, now what we're going to do is we're going to step out, and you can see that at the beginning of this, we stored some system parameters, our mode, our feed mode, and we're restoring those before we jump back out of the subroutine. And then here, we're updating the actual G55 system variable offset. And inside VERICUT, you can see that it updated that value. So the next time I jump into this sub and run it, I can see not only am I validating the feature diameters, I'm also validating my offsets and my positioning correctly. And so here, for the second nest level, I just wanted to show that we support G10 commands to do the same thing. So this is controlling my G55 for my next row. And then the simulation continues, and then we're done. All right, at this time, the demonstration has went long enough. Hopefully you're still awake, and we can open it up to questions, if there are any.
Yeah, there's 2 so far, and you may have answered this already. How do I check a missing bracket if or in an if statement?
Yep. Okay, so just to clarify here, let's purposely break this while loop here. I'm going to save that. And so without even playing the simulation, I'm just going to do a syntax check. And right out of the gate, VERICUT found where that syntax error is. So now I can come directly in my NC program and add that bracket back, save it, and then check all. And we can see that the missing bracket is no longer a problem. All right, any other questions?
Can and how do I verify the machine hole die?
So once we've machined the part, let me take this stop condition off. Take this one off. Okay. I'm just going to come up here to X caliper and check hole depth, and that's 300 thousandths. Then we can check the spacing between those to see that all of our parameters are being met without using any material.
Okay, and then there's does this work with Panic virtual y-axis?
Say that again.
I might be pronouncing it wrong, but does this work with Panic virtual y system or virtual y-axis? It's in the questions. If you can...
Oh, I see. Yep. Maybe we could clarify what the question is. as far as this is our machine here, right? So we have the machine structure, the kinematic structure that we already talked about, and then we're writing the macro program for it. So I'm not sure if that answers Rick's question, or if he could clarify there. So, yep, whether or not it's virtual or not, for MacroB programming, we're obviously going to start with a machine and control configuration that has our kinematic structure, so we can validate the same stuff: collision checking, travel limits, and verify our feature information. So,
that is all the questions that I have.
Yes, I just didn't, basically helical interpolation. I didn't demo that just because I was being a little bit lazy in my macro program that I wrote here. So. All right. Any other questions, or you can actually enter comments as a question if you want. If there's, you see any use to while loops, if statements, verifying and validating these. I can open my G-code logger and see that what the variables were. So while one, here's my while loop, do two, and we can see the variables that were referenced without actually trying to hit cycle start and run those on the machine. Oh, and I forgot, I was supposed to show this slide. Sorry about that, ladies and gentlemen. If you guys have any questions or want to contact CGTech for further information, we've got our phone number there at 949-753-1050. And then you can always contact us through the website, and that is here at cgtech.com. You can see our homepage. And then there's the products page where you can look at the full product line and see everything that we offer. And then, of course, if you ever have any questions or need support, you can contact VERICUT support, and we'll be happy to help. So if there aren't any more questions, then I think that will be it for me. I appreciate you guys taking the time out of your day to be a part of this webinar, and hope that you have a great rest of your day. Thank you.